Thank you very much. So my name is Arthemy Kiselev. I'm very grateful to the organizers of this event for a possibility to share recent results on star products, on very high order expansions of star products. Thanks for coming. The results which I'm going to report tonight are joint with R.Buring, and this is partly illustration of fundamental concepts in mathematics, partly experimental mathematics. Today I have chosen to talk about combinatorics and arithmetics for physics. So what star products are? On the one hand, we have classical dynamics, classical mechanics and Poisson dynamics. Then at the start of 20th century, it was understood that we need non-commutativity and we need quantum mechanics. Quantum mechanics, where our usual coordinates and momenta acquire different nature. They become operators acting on a Hilbert space and so on. So there is a very big gap. And in the end of 1920s, Hermann Weyl suggested, no, this is a very big gap. Let us still have something close to classical mechanics. But let us postulate, let us analyze what happens if the coordinates and momenta, if the dynamical variables in our Hamiltonian mechanics, if they become non-commutative. But we preserve the associativity. So the concept of Hermann Weyl, which was developed basically immediately after the war, in the end of 1940s, and until now it develops. It is transitional between classical mechanics and quantum mechanics. And we learn that there are domains of applications in physics for that, specifically very high energy optics. When you send 1 million waves, 1 million periods of electromagnetic field, this is just usual optics, wave optics, and the optomechanical analogy, a canal, and everything that we had for particles in usual mechanics. If you send 1 period from a laser, then you have pure photonics, and you just send a quantum. But if they learned some 30, 40 years ago to send 2 or 3 periods. So it is not a quantum, it is not many waves. So when it is 2, 3, 5 periods, then physicists in very high energy optics, they do phenomenological models which are governed by star products, by non-commutative associative star products, which are in between classical mechanics and quantum mechanics. So today my task is to report the state of the art in high order expansions which are usable in physics applications, in technical physics. I shall report a very high order expansion for a very particular class of brackets, linear or affine coefficient Poisson brackets. And we shall discuss what is peculiar about those results in the context of what is known. First of all, today I shall stay within deformation quantization, how it is tracted, how it is dealt with after the pioneering work of Kontsevich from '97. That is, on the one hand, suppose that on an affine, for simplicity, finite-dimensional Poisson manifold, in the algebra of functions, we have our usual product. And now there are 2 reciprocal tasks. Let us deform our product with a formal deformation parameter h into a power series with a tail, into a binary operation which on the space of formal or C power series is associative but not obliged to be commutative. In one direction.
You have powers of h bar in your sum or not?
Yes. Sometimes you just incorporate them into notation, sometimes you even indicate the factorials separately. That is a matter of taste. On the one hand, if such a star product is God-given associative, then you learn that the skew part, the symmetric and skew antisymmetric part of B1 is a Poisson bracket. And reciprocally, suppose that we want to start our star product by deforming the usual product towards a given Poisson bracket in the leading deformation term. Theorem, we can always construct the entire formal power series of that star product in such a way that it is associative at all orders. There is more in the result from 97, but for us, primarily in this talk, existence is important, and moreover, the procedure of obtaining this star product order by order perturbatively is constructive by using the graph language. That is, instead of writing formulas, we shall draw directed graphs. And today I shall report on the construction of star products using graphs, on the construction of star products using graphs by using the software to deal with, as we see, hundreds of thousands and millions of graphs as we go to orders sufficiently high. As for the software, part of the software which we use has been developed by R.Buring in the course of years. Specifically for graphs with real coefficients, alternatively, there is a work, a brilliant work of Banks, Panzer, and Pym from Oxford, from the group of Francis Brown, who some 5 years ago expressed the coefficients or effectively wrote a program expressing the coefficients of these graphs encoding the expansions of star products in terms of Riemann zeta, multiple zeta values, MZVs. So these two software packages, which are available, freely available, they complement each other, and we have checked and partly corrected some of the results of our colleagues, and by using the software of our colleagues, we manage to advance, and I present the results now. So the language of graphs is as follows. I shall very briefly recall some perfectly standard material, and then I shall outline what is known, what was known so far. Instead of writing analytic formulae, let us, instead of writing derivatives in some local chart on our affine manifold, transitions are affine, at most linear plus shift. Let us draw decorated edges decorated by summation indices running through 1-2 dimension of our manifold. We shall deal with graphs whose vertices are inhabited by copies of a Poisson structure. That is, a Poisson bracket is a B derivation. I have drawn a B derivation with an ordering of edges. One is left and one is right. That is, strictly speaking, the combinatorial structures which I am using are more than graphs. They are graphs with ordering of outgoing edges. So this picture really corresponds to a Poisson bracket, and that is what you deal with every such what you do with every such graph. You decorate all the edges, every edge with its own summation index. You take the product of content of all the vertices, be they aerial vertices and sinks, and you take a sum over all summation indices. In particular, here are examples of graphs in the calculus which we use in deformation quantization. This is an example of a graph. This is an example of a graph. I do not indicate which arrow is left and which arrow is right, and therefore I write plus minus just freely. FGH, FGH are functions on my manifold, FGH are functions on my manifold. So this is a trident graph which corresponds to the Jacobiator, to the left-hand side of our Jacobi identity for the bracket which we have on our Poisson manifold. And another example is from the pioneering paper 25 years ago. We celebrate the star product of two test functions is, well, you do nothing. You just take a usual product in the sense of our original algebra on the original manifold, plus the Poisson bracket in the leading deformation term, plus the Moyal term with second order derivatives of the arguments, plus something which starts working when our bracket is not any longer constant coefficient. This and a peculiar term with an I, plus omicron of h squared. So we can have two cycles quite easily, and the big secret is that at order 4, two cycles become dominant.
Sorry, I am lost by something which is perhaps easy. Why you have sometimes a bar above Fg and sometimes not? There is a meaning to it, or? For the term of order 1, 2, and at the end you put a bar and not the other ones.
Beg pardon. Where is a bar?
H bar 2 over 3.
Omicron of h2.
Just above Fg. For example, in order at degree 1. Degree 1 is H bar. Yes, you put a bar above Fg.
Where? No. Let me answer. Thank you very much for your question. This was my currently next idea. All these graphs exist in the upper half plane.
Okay.
This is the absolute the boundary of the upper half plane, so that the stated fact is that the coefficients in the h bar expansion, these coefficients can be, there is a formula for them. In terms of hyperbolic Lobachevsky geometry in the Poincaré model, in particular in the upper half plane for the hyperbolic plane with hyperbolic metric. In earnest, the edges should all go along parts of geodesics in the upper half plane with respect to the hyperbolic metric. So Maxim has revealed an intrinsic relation of coefficients in this expansion to the hyperbolic geometry. Graphs are actually realized with respect to the hyperbolic geometry of Lobachevsky plane. Here I use the upper half plane model. You can use the Klein model. You can use the Poincaré model in a disk, and so on. Thank you very much for the...
So you have also this kind of upper plane for the h bar of the degree 2/3? The next term.
Yes. Well, yeah, the arguments of the star product are always on the absolute. The sinks are always on the absolute, if for the sake of speed I did not always draw them. Okay, so let us pay attention to the modality in my statement. There is a formula according which we can in principle calculate the weights of these graphs in this expansion. The real life only tells us that it gets increasingly more and more difficult to actually obtain the exact values of these integrals over configuration spaces of points in the upper half plane, just encoded, just corresponding to our graphs. So there is an industrial activity of building, of producing higher order expansions of star products. So let us see the timing. 97 h bar squared, the formula which we have here. Then h cube expansion. For generic Poisson structures, I did not ask you what your favorite Poisson manifold is. I did not ask you what your favorite Poisson structure is, and I didn't ask you even what the dimension is. So Penkava Van Heck.
Just a question.
Yes.
Do you consider only parallelizable spaces, M?
Just arbitrary affine Poisson manifolds. Arbitrary. Okay, in cubic expansion, 1998 by Penkava Van Heck. That was not the authentic Kontsevich star product, but that was a gauge equivalent to the authentic Kontsevich star product. Authentic means that all the coefficients are defined by the formula, by the integral formula. H bar to the power 4, 2017. In the work of R.Buring. Then there was a breakthrough, h to the power 5, h to the power 6. It was 2018 by Banks, Panzer, and Pym. The only thing is that they did not certify the associativity. Order 4 associativity was certified, the absence of error was guaranteed. It was later, by using the software of R.Buring, that the associativity was certified up to order 6 for generic Poisson structures. Yes?
Important point, there are actually two formulas. There are two formulas for weights.
Yes.
One is better, one is worse.
Yes. First of all, today, okay, disclaimer. Today, I report about star products in the shape they are obtained by using the graph language of Kontsevich only for harmonic propagators, for the weight formula from the original paper of 97, but not the Kontsevich formula with logarithmic propagators in the paper from 1999 in operas and motives in deformation quantization. Disclaimer 3. I produce star product expansions only in the authentic gauge that is corresponding to the classical weight formula before any gauge transformation is done with them. In particular, we do not gauge out this graph at order 2. However, yes, there are many ways. There are many ways to introduce the weights of whatever graphs suitable at whatever order, harmonic originally, logarithmic then, interpolating family then. I completely agree. Thank you.
Yeah, but logarithmic it kind of seems to be the best. Yeah, so the rest should be.
Probably I shall come here again and I shall pronounce a copy of my talk with different coefficients, of course. Quite naturally. So look, order 6. And order 6 is already on the verge of what an ordinary desktop computer can do without any exaggerations. And now we discover, if we want to advance, we discover that for particular classes of Poisson brackets, we can advance further. And there exists another theory besides, totally independent with respect to the Kontsevich graph language, specific for, in particular, linear or affine Poisson brackets. Linear, for instance, on the duals of Lie algebras, or affine Poisson brackets, which are also very natural. They correspond in mechanical systems to switching on the external field, like electromagnetic and gravity. We can have a top in vacuum, and we can have the heavy top in gravity field, and the Poisson bracket changes a little bit. It becomes affine. And look, in the handouts, which are also available online on the web page of this conference, we see a table of how many suitable graphs, relevant graphs, we have at different orders. In particular, alone at order 7, we should, in principle, calculate the weights of approximately 2 million graphs, which by pen and paper, as we do it at order 2, is unfeasible, but 2 million is already a lot. However, if we consider not generic Poisson structures, but affine, what changes? You see that the aerial vertices of our graphs sitting inside the hyperbolic plane, they are inhabited by copies of Poisson bracket coefficients. It means that whenever every arrow coming into a vertex means that the content of that vertex is differentiated, it becomes totally pointless, useless, trying to differentiate a linear or affine expression too many times, namely 2 or 3 or more times, because the result would be identically 0 if you differentiate an affine function 2 times. Therefore, whenever we know in advance that our Poisson brackets have linear or affine coefficients, we are allowed to expand the star product only with respect to graphs where the incoming degree of any aerial vertex, but not a sink. Sinks are whatever they want. They acquire whatever number of edges they want. The in degree of aerial vertices is bounded by 1. And then there remain only a tiny proportion, an exponentially lower proportion of graphs, namely of order 500. And that is completely manageable. And that we did. That was done in this calendar year, 2022. There are many natural ways to constrain the weights of Kontsevich graphs in this approach to star products. We briefly recall methods to constrain. I do that in order to explain something very non-trivial and helpful in this domain of science. So methods to constrain the weights of graphs built of wedges. Our graphs are built of wedges, which means that we are actually dealing with graphs built of Poisson structures, which actually means that our star product, regardless of coefficients, which we seek, amounts to differential polynomial expressions with respect to the coefficients of our Poisson bracket. So first of all, elementary properties of these weights. Specifically, two graphs standing on the sinks can be mirror copies of each other. In that case, we do have a very natural relation of the weight for this graph and for that graph. So we can study only basic graphs. If you know the weight of one graph, then you know the weight of its mirror reflection, and so on. Secondly, multiplicativity. Not, very strictly speaking, for the definition of weights of graphs in 97, but for a formula where just one factorial is missing. So for weights which are in one-to-one correspondence with the originally defined, for them the weight is multiplicative. Namely, if we know the weight of such a graph, and we know the weight of such a graph, and we identify their sinks, then we know the weight of such a graph, which is built by multiplying these graphs over the sinks. We just identify their sinks. The rest, the graphs know nothing about each other. Thirdly, that is the most interesting thing, cyclic weight relations. Cyclic weight relations by Felder-Willwacher from ETH Zurich, based on the work of Scheuchert. So originally, in the year, I believe, 2000, there was a paper by Boris Scheuchert about cyclic cohomology. And in the year 2008, in a paper, very strictly speaking, on a different subject, I'll tell you now what it was about, by Felder and Willwacher, in one of the appendices, they suddenly reinterpreted a result about cyclic cohomology in terms of a very peculiar property of Kontsevich graph weights. Specifically, consider a graph theoretically showing up, if its coefficient is non-zero, in the expansion of a star product. Do the following. Look at your graph and start redirecting edges between aerial vertices, your favorite edge, two favorite edges, three favorite edges, and so on, up to basically all, to the leftmost sink. So you obtain new graphs with their weights. Or in the original graph, make a cyclic permutation of sinks. Here we have two sinks, so just swap them. If there are three, which is also possible in all that theory, just permute them cyclically. There exists a class of linear constraints relating the weight of your sinks permuted graphs and the vivisection redirected edges graphs. And that system of relations we discover gives us very high rank linear algebraic systems. So that if we start with many unknown weights, there remain very few master parameters. Moreover, look, we are redirecting edges between aerial vertices to sinks. That is, we do not increase the indegrees of any aerial vertices. There was an incoming edge to an aerial vertex, but now this edge goes to a sink. So the indegrees of aerial vertices either stayed the same or decreased. Yes. So here are the sinks. here is the leftmost sink in 0 on the real line. Here is your favorite edge from an aerial vertex to an aerial vertex. And here is a graph where all of this happens, and here is a weight of this graph where all of this happens. So this weight up to permutation, cyclic permutation of sinks, is a weight of another graph gamma prime where this edge is now sent instead of this vertex where it came to the sink 0.
But will be other edges close to sink 0 as well?
There could be, all the rest remains as it was.
Just one edge you said?
One or two or three, okay. or all.
Starting from a given vertex, yeah?
All edges in our graph. Any collection of edges you redirect to the leftmost sink. And there is in Catania-Felder 2008 such a beautiful claim, and we get Catania-Felder. Felder-Willwacher. Sorry. Okay.
And does it work for logarithmic propagator as well?
Oh, let us discuss it. Let us discuss it tomorrow at 10. Right now, I don't remember. So once again, practical engineering conclusion: the rank of this linear algebraic system, in whatever ways to constrain the weights of graphs, is enormously high. It is a very profitable activity. And fourth, associativity as it is. Associativity as it is for specific classes of Poisson structures we constrain, and for generic we constrain. We know how to do it theoretically and practically. And now comes an observation. I promised you to tell you what Felder-Willwacher in 2008 originally was. That was a very nice paper telling us that on 7 aerial vertices, that is near Planck constant raised to the power 7, there is a graph. It has all in degrees at most 1. So it will persist in an expansion for linear or affine Poisson structures. Totally innocent looking graph. And Willwacher proves that its weight up to rationals is an affine expression with a zeta of 3. And about zeta of 3, we want to know more. Zeta of 3 squared divided by pi over 6. Is it rational or irrational? Of course, it is irrational, but we don't know. Is it algebraic or transcendental? We don't know. So Riemann zetas also sit in the Kontsevich weights already for harmonic, non-logarithmic, for harmonic propagator in the integral formula. And that is a given datum. Nobody promised that our coefficients are rationals. They are whatever real numbers containing zetas. And now, after Banks-Panzer Pim, it is understood that the higher you go in the expansion, the higher arguments in the Riemann zeta you get. There is a balance between the order of Planck constant and the argument of zeta. You do have zeta of 3 starting order 6, then you will have zeta of 5, then sooner or later you will have zeta of 7, and so on. So that is...
you get zeta of 3 for 3 things.
Okay.
Already, yeah.
Even depending on our taste, better or worse.
But you get MZV, no?
Multiple zeta values?
Multiple zeta values, yes. That is exactly the essence of Banks-Panzer Pim in Inventiones. In the archive, it is in the last day of 2018, 30th of December, last of December and published in Inventiones in 2020. And now, thanks to our activity, correction has been published recently about our verification of their numerics. So two numerics verify each other. And now I just sum up our results. First of all, now that we understand for affine Poisson structures, everything works to collapse our system. You see that, for instance, at order 4, for generic Poisson structures, following this scheme in our constraint of the next order of expansion weights, we drop down from 10,000 unknowns to only 10. And then we calculate by Banks-Panzer-Pym, roughly speaking, by direct integration of the Kontsevich weight formula. In the affine case for order 7, it works even better. So in order 7, for generic Poisson structure, star product is not known. That is unfeasible. For affine non-quadratic affine Poisson structures, we know it. So result 1, we know the affine star product. Perfect. It contains many coefficients with zeta. So rational part times zeta of 3 times rational coefficient. On the other hand, if we follow a completely different line of constructing star products, that line started 50 years ago with Berezin. It is all based on the study of Lie algebras, Lie groups, universal enveloping, Campbell, Baker, Hausdorff. Then Simona Gut worked there, De Wilde Lecomte, Fedosov, and whoever else in the class of very particular linear Poisson brackets. There is a result that all the coefficients for linear Poisson brackets should be rational. So we have two statements. At order 7, all coefficients should be rational. Many coefficients contain zeta. So on the other hand, one could claim, well, Berezin and company did not make claims about Kontsevich star product. Maybe it is a gauge equivalent. Maybe it is different propagators. No. We discover the following. Look, result number 2. In the star product for affine Poisson structures, when we get Riemann zetas, zeta of 3 at order 6 already from Banks-Panzer-Pym, and at order 7, all these occurrences of Riemann zeta stand near some graphs. Now let us look at all the graphs standing near Riemann zeta. They all merge into Jacobi identities left-hand side and its differential consequences. That is, whatever Poisson structure you try, affine Poisson structure, and you write an analytic formula of the star product, not by using graphs, but specifically just write an analytic formula. There will be no zeta in it, even though in the graph formula there are Riemann zetas in the coefficients. Why? Because the Jacobi identity holds for your favorite Poisson bracket, and Riemann zeta is multiplied by 0. Moreover, even in the purely rational part of coefficients in the 7th order expansion, really much, I shall now tell you, really much is collapsed, is assimilated into differential consequences of the Jacobi identity. So that, on the one hand, there was no contradiction between the two claims, only rational, and here are possibly irrational, likely irrational. There is no contradiction. It is all modulo the Jacobi identity. Secondly, in the 7th order expansion, in the entire formula, we have 1,423 non-zero coefficients, which is also really few. Kontsevich star products in this language are really not in general position with respect to the number of graphs. No. They are very peculiar structures. And after you use the Jacobi identity, there remain only 326 non-zero coefficients. And that is what we sell to photonics people. Seventh order in Planck constant, only 300 terms. It is manageable in whatever phenomenological model they use in high energy optics.
Use just universal development algebra.
Fortunately, they start with linear Poisson brackets because it is already non-constant coefficients, but still not so complicated.
Campbell-Baker-Hausdorff. You don't need to go to this thing. It's really meta, yeah.
They have a closed community. They just sit and they borrow star products from whoever gives them to them. There are reviews from 1980s and there are very recent reviews from photonics people, from technical material, nonlinear optics people. Just they use whatever formula is given to them, whether it is Campbell-Baker-Hausdorff or whatever.
Anyhow.
Okay.
You have only one.
Maxim, the point is that irrespective of photonics guys, we have not seen the seventh order expansion even by using Campbell-Baker-Hausdorff. It is true that it can be constructed. One thing, who constructed it? I believe nobody. Secondly, when you have constructed it, it is a good idea to verify the absence of error. And here we do not use one method. Here we use many methods checking each other. We implant many ways to verify the result of our doing. So in principle, one can use one method, Campbell-Baker-Hausdorff. Here we use the plurality of methods. They all check each other. And we check those noble guys from Oxford, from the Francis Brown group, and they publish corrigendum. And the last result number 3. So expansion, collapse of expansion to a tiny formula, it is like an accordion. You just compress it and the result is very small. Third result is the method of associativity. I have told nothing about it. In principle, it is possible to have that, and references, all the proper references in the paper I report. The mechanism of associativity up to and including order 6 is different in the way how it works from order 7 onwards. Of course, the associativity is guaranteed in this language by the formality statement. But the graphs, the differential consequences of the Jacobi identity, which we need to express the associator up to and including order 6, they are all immediately obtained from the associator itself. Just collapse one edge and you will get proper graphs. Starting from order 7, neither for the affine case nor for generic Poisson structures are the graphs only from the associator enough. You need more graphs in the right-hand side and then expand them to graphs built of wedges in order to balance the associator and establish the associativity. So 7, so there is one threshold, moral threshold in the star product theory, 3. Just 2 is a very low order, 3, some effects start showing up at order 3. Well, Maxim tells us Riemann zeta show up. 7 for harmonic weights in the authentic gauge is also a threshold. Up to order 6, the associator contains all the suitable graphs. Starting order 7, more graphs are needed, and we explain all of that in detail. We could discuss it. So that was all 3 results: high order expansion, collapse of expansion, and the mechanism of associativity, which we confirm and which we verify. Here they are. Thank you so much.
Is it possible to predict the asymptotic growth of the BN, the number of nomials or graphs that they involve?
the number of graphs essentially having non-zero coefficients, I've got no idea about the growth.
Factorial, yeah, it's factorial loss, but for graphs, there was a paper by Andler and Sahi many years ago for linear brackets, for the algebras. They make estimates it was really convergent. They have convergence result, they use it.
You mean that generating function associated to this?
Oh, no. The whole thing is actually will be not only asymptotic series, it will be actually.
Okay.
Yeah.
Mm-hmm.
So the number of graphs grows like this, and the number of effectively used graphs grows like this.
Yeah. Naive question. What about the dual law of stacked products? There is something to do with the deformation of multiplication of integral, because zeta 3 do appear on the coefficient. So there is something to say about the co-products of stack. No?
Frankly speaking, what is the question?
The question is, what about the co-products of stack products?
Co-products.
No idea. Well, it is just my ignorance. Not that the question is meaningless, it is just my ignorance.
So the zeta do appear to have some deformation of shuffle of like that.
I believe the question is good, I don't know.
Can you, thank you, great talk. Can you explain how Riemann zetas appear?
Reference surfaces. Banks Panzer Pim, Inventiones Mathematica, 2020. It is a 70-page paper, so I believe it is a good reading. Just whatever reasonable questions about how they appear, why Kontsevich integral formula is really expressible, the entire paper is precisely about that. So Banks Panzer Pim, Inventiones 2020, correction 22. Thanks. Thank you so much.